As we all know, the formula to find a gradient of a straight line, find A and B, is m of AB equals y2 minus y1 divided by x2 minus x1. However, this could not be used on a curve. So if we draw out a curve like this, we could know this. This is A and B. We could notice that as we move along the curve from point A to B, it gets steeper. This is not a straight line, so we cannot apply this formula onto here. Therefore, in order to find a gradient of point A and B, we have to find a tangent line to the curve at point A or B. To zoom out this part, there's an infinite number of gradients as you move along the curve. At A, the tangent line could be this. At B, the tangent line could be this. So we can only find a gradient of a curve at a specific point. So how do you know if the tangent line is accurate when it is drawn?
So here's the differentiation of two functions together. And the first function is 4x squared. And the second one is x equals 1. Sorry, y equals 1. And yeah, we plus them together, and we're trying to find a derivative for that. Then here we go. We can just simply use the a and x rule and the a and x rule. So that comes there as a, and the power goes down 1, so that becomes 8x. But as for 1, as it gets derived, it's taken away. Okay, let's move on to a harder question. You can see that equation there. We convert that into that. Yep, and that into that. So that's easier to derive. That times that equals minus 1, and the power minus 1. So it's from a half to 3 over 2. Same for that one. Go down 2 becomes minus 6. That power goes down 1. It goes minus 3, and that's the answer. This one's absolutely correct, but this one would be more correct or authentic, whatever. More respected, whatever. Yeah, and that's just thirds. Okay.
Now I'm going to show you how to find the first derivative of a function by differentiation. So this is our function x squared plus 3x plus 5. To find the derivative of this function, you take x squared and you move the index in front of x, so it becomes 2x, and then you minus the index by 1, so 2 minus 1. This gives 2x to the 1, which is 2x. And then the next number in the next component in the equation is 3x. To differentiate 3x, you follow the same principle. But remember that x means x to the 1. You times 1 by 3, which gives 3x to the 0, which is 3. And 5 is a constant, so when you differentiate a constant, the answer is always 0. So it's negligible in our differentiated function. Therefore, the first derivative of the function is 2x plus 3. Here's a general formula to work it out. Here are some reminders when you differentiate the first derivative. You have to always turn x into something that has x and the index of x. For example, square root of x is x to the half, and cube root of x is x to the third. And for fractions, 1 over x is x to the minus 1. 1 over x squared is x to the minus 2, and 1 over the square root of x is x to the minus half.
Second derivative is the differentiation of the first derivative. So if we have the function f of x is at y equals axn, so the differentiation of this f dash x, or people call it dy over dx, equals an to the power x and x to the power n minus 1. This is the first derivative. The second derivative is f dash dash x, or people call it dy, just call it this, equals n minus 1 an x n minus 2. Just to avoid confusing you, this is a real example of this. For example, to differentiate this, or dy over dx of this formula, this is equal to x plus 1, x to the power minus 1. So it's dy over dx of this is 1 plus minus 1 x minus 2. Or people could use it 1 minus 1 squared. And the second derivative of this is equal to, because this minus 2 times minus 1 is 2. This one is cancelled. So plus 2x to the power of minus 3. Or you could write it as 2 over x cubed. So this is its second derivative. You could find it useful if you look at page 115 on your book. That's it.
I'd like to show you how to find the tangent. You can use differentiation to find the equation of the tangent line to a curve at a particular point. Bearing in mind that a tangent is a straight line, therefore the equation is y equals mx plus c, m being the gradient of the tangent. Here's an example. To find the tangent at P, 3, 9, on the curve y equals x squared, you do the following steps. First, you differentiate to get 2x. And then at point 3 and 9, you plug x equals 3 into the differentiated function to get 6. And m equals 6. 6 is the gradient of the tangent. You apply this formula down here in order to find c. In order to find c, you plug 3 and 9 into the straight line function to get 9 equals 6 times 3 plus c. And then you work out c. And c equals minus 9. So in the end, you get the gradient of tangent, which is y equals 6x minus 9.
How do you find the equation of normal? Firstly, you want to find the equation of tangent. And to find that, you find the gradient of the tangent by deriving the equation. And deriving the equation, you will have that equation. Let's see, from that, I converted it into x to the power of minus 1. And minus 1 comes down there. It comes minus 1x to the minus 2 as power goes down 1. Okay, 2x, and that's the answer for the first derivative. And to find the gradient, you simply sub in the x value. So 1 sub into that. So 1, and that's the answer. So the gradient is 1. And so you want to find the gradient of the normal right away. So how do you find that? We put it as a fraction, let's say. So 1 over 1. And then you flip it over. And then put a minus sign on it. And that's the new, and that's a gradient of the normal. Same as here. If you have a gradient of tangent being 2, just put it as a fraction. 2 divided by 2 is 1. 2 divided by 1 is 1. 2. And then you flip it over, and you have that as a gradient of the normal. And I did, okay, and then back to the answer to the normal to this. Let's see. Okay, so minus 1x, see, now we sub the values in, 2 being y, and then 1 being 1 for x. 1 times minus 1 is what? Minus 1. Here's 2, so c equals 3. And y, the equation then equals y equals minus x plus 3. That's how you find the normal. Equation of the normal.
Now I'd like to introduce you to maximum and minimum points. Here are some features of maximum and minimum points. They are called stationary points, and when the first derivative equals 0, it is at the stationary point. And to determine the nature of stationary points, we use the second derivative, which is d squared y over dx squared.
Right, so we use the first derivative to find stationary points, and stationary points are minimum, maximum, and point of inflection. So we can see here that's the derivative of that equation. Let's take that equation, x to the power 4 minus 8 squared, 8x squared minus 3. So find stationary point. We derive that equation into this equation, and then make that equal 0. Then you'll find the stationary point. You'll find the x coordinates for its stationary point. Okay, and the x coordinates are plus 2 and minus 2 and 0. And moving on to here. So here the criteria to be maximum, minimum, or point inflection. Okay, your second derivative with your subbed x in, then that whole equation must be equals to, if it's less than 0, it's maximum, it's more than 0, larger than 0, it's minimum, it's equals to 0, it's point inflection. There you go, if you can see that. Okay, so that one I subbed 0 in, and it was less than 0, so it's maximum. And that one I subbed 2 in, and it's minimum, because as you can see, as calculated, it's plus 32, so it's larger than 0, that's minimum. So to find the point of inflection, you don't really need to know the x value, but you can just put the whole second derivative as 0, and just work your way through. See that 16x go over to go over to the other side, it becomes 16. Then as you can see, 16 over 12 is the x squared value. The x value would be 4 over square root of 12. That's x. Yep, that would be the point of inflection. And here's actually a graph for it. Yes, you're able to see. For this, see that 0 to maximum, 2 is minimum, minus 2 is minimum. Around there is a point of inflection around here. Or is there at all? Yep, there should be point of inflection somewhere there. And it's around 1.5. Say that's 1. It's around there. Anyway.
In order to define the maximum and minimum point of this equation, this is an example. Okay. So first, you differentiate it to find this step. It's called differentiate. First derivative, and then you make that equal 0, because remember at dy over dx, the stationary point is at the stationary point, so it's 0. And then you can use your GDC or factorization to get the x value of x equals 5 and x equals minus 1. And then you plug x equals 5 and x equals minus 1 back into f of x to get the y value, which is minus 99.999. for x equals 5 and 9 for x equals minus 1. And then you find the second derivative by differentiating the first. So it's 6x equals 12. That's the second derivative. And then you plug the values of x into the second one to get 18 and minus 18. As I said before, if the second derivative is less than 0, then it is a maximum, and if it's more than 0, then it's a minimum. Coming back to the same example, I would like to show you a different method. Sometimes this is more useful, and sometimes the other one is more useful. In this one, we're going to examine the gradients on each side of the x values. So first, you arrive at the x values by differentiating and then solving it. When you have come up with the stationary point, you will then draw this table. You put x and then the value of x that you found in the middle, and then you choose 2 points. That's more, and then less than that x value, and then you plug this and this into dy over dx. You do the same for the other point. If the number is negative, then the gradient is like this, and if the number is positive, then the gradient is like this. It's at 0 then, so it's that. And from this to this, you can see that it's a minimum, and from this to this, you can see that it's a maximum.
Now I'm going to introduce the gradient as the rate of change. The gradient of a curve is given by dy over dx, or it could be seen as difference in y divided by difference in x. So we could say that derivative of dy over dx is the rate of change of y with respect to x. A common rate of change connects to the velocity, the displacement, and the time. As you can see on this graph, where distance is plotted against the time. Distance at this point is y, and this one represents the x. In the line PQ, it represents the distance traveled between the 2 points P and Q. The length PR in here represent the time taken to travel this distance. So the gradient of the line PQ represents the average velocity of the body during time interval. Therefore, we could find the velocity v at time t could be given applying the knowledge of differentiation. We could say that v equals ds, which is the displacement, the distance, over dt. Very similar to that idea, you could also find the rate of change of the velocity with the respect of time, which is called acceleration. Well, in here you can see the graph with the velocity plot against the time. So therefore, you could find the acceleration using the similar method by taking dv, which is the velocity, over dt, which is the time. Stationary point is when dy over dx is equal to 0 in order to find a minimum point, a maximum point, or a point of inflection of a curve. A second derivative can be used as an easier way of determining the nature of any stationary point. Once you have established where there is a stationary point, the type of that, which is minimum point, maximum point, or point of inflection, could be determined. For example, if the second derivative is larger than 0, is a minimum point. If it's smaller than 0, it's a maximum point. However, if it's equal to 0, it's a point of inflection. To easier you in with an example, y equal x cubed minus 9x squared plus 15x minus 7. Therefore, to differentiate it, we have this as the first derivative. To find a stationary point, we put that equal to 0. And step by step, we're able to find x equals 1 and x equals 5. But what we don't know is which of them is maximum point, minimum, or a stationary point. Therefore, we differentiate again to find a second derivative, which is 6x minus 18. Therefore, we sub those number onto here. So at x equals 1, for the second derivative, it's equal to minus 12, smaller than 0. So we could apply, so to remind you to this one, it must be a maximum point. Whereas at x equals to 5, the answer is 12, which is larger than 0, so it must be a minimum point. So we could conclude that with this equation, it has x minus 1 as a maximum point and x minus 5 as a minimum point. Done.
So at the second derivative, if f dash dash x is bigger than 0, it is the minimum. And if f dash dash x is smaller than 0, it is the maximum.
Move on to the increasing and decreasing function. You can review that in page 132 in your book. Ta-da! Okay, a function is increasing when the y value increases as the x value increases, as you can see here. From this point to this point, we can see that from here the y value increases as the x value increases. We also work with this one. Increases, as also with this one. Increases. It also increases even though the rate of increases reduce in here. Or it could be like this. When the y value increases and the value of x increases for x larger than 0. So a function of gx is increases when x equals a if fa larger than 0. Put it for an interval. So here's a graph. Interval is just a part of the curve. So if a function is increasing for the interval shown, it may be increases or decreases where else, but however, for only in this interval is increasing. So in reverse, we have a decreasing function. So y value decreases as the x value increases, because we know on the graph the x so cannot decrease. So in here, you can see that the y value from here to here is decreased. However, in here it's still increased. So if we put it in this context for another interval from here, so we say from here to here, from this point to this point is a decreasing function. Ta-da!
You may be wondering why does finding the first derivative could be useful. So here's how it is useful. For example, we have the shape triangle A, B, and C. And A and B plus B and C is always 6. So the question asks you to write down BC is AB equals X and find the maximum area of ABC triangle. So here's how you do A. Quite simple. Since you know that A plus B equals 6 and AB is X, you sub X into AB. So X plus BC equals 6. Therefore, BC equals 6 minus X. The formula to find the area of a triangle is a half times BC times AB. Therefore, a half times 6 minus X times X. And you get this formula down here. Using differentiation, it's dA over dx. Since A is the function, is the equation that we're trying to find the maximum for. So we know that the maximum occur at
when dA over dx equals 0. And when to differentiate dA over dx, we use this function. When you differentiate it, it becomes 3 minus x. dA over dx equals 0, therefore 3 minus x equals 0. Therefore, x equals 3. The maximum area is when x equals 3.